All right, moving right along with sulfur nucleophiles. Ketones and aldehydes react with thiols virtually the same way as they react with alcohols. It's the exact same mechanisms. We just have a couple extra things that we can do with a cyclic thioacetal or a thioacetal. But let's just dive in a little bit. Thioacetals can be converted to alkanes when reacted with rainy nickel. No mechanism for this one. If I wanted you to do the mechanism for a thioacetal formation or a cyclic thioacetal formation, it would be the exact same curved arrows as our oxygens, right? Sulfurs and oxygens react the exact same way. And so with sulfurs, just think this extra step of rainy nickel to convert and reduce a thioacetal to an alkane is solely for the thioacetal. Rainy nickel will not reduce an acetal, a typical acetal, an oxygen acetal to an alkane. It just won't. Oxygen's not as reactive as sulfur here. So rainy nickel is a great reaction for taking a thioacetal to an alkane. You can see it there in a synthesis. It allows for the reduction of a ketone or an aldehyde to an alkane itself. Let's get into hydrogen nucleophiles. We've been playing with lithium aluminum hydride and sodium borohydride as hydride delivery reagents for a while. So we should have remembered this reaction from chapter 12. Let's just go through the mechanism one more time. Again, they are carried out under basic conditions because either lithium aluminum hydride or sodium borohydride is essentially a hydride delivery device. Remember, lithium aluminum hydride is a strong reducing agent. Sodium borohydride is a more mild reducing agent. Basic conditions. So first step of the mechanism is a nucleophilic attack. That hydride H- will attack the carbon of the carbonyl, kicking up a lone pair. Water can then be our proton transfer reagent. This is where we're going to most likely see our first aspect of unsymmetrical ketones forming a new chiral center. We talked about this at the very, very beginning, where we have something that is sp2 hybridized, so trigonal planar, and now we have something that is sp3 hybridized, potential for chirality. So if you have two separate different R groups on your ketone. This won't happen for an aldehyde, right? Because especially with lithium aluminum hydride, you're adding H-1, right? You're adding a hydride. So it has to be an unsymmetrical ketone specifically for this reaction. It happens also with sodium borohydride. Those reagents are interchangeable in this chapter. So be very careful. Racemic mixtures always will form if we form a chiral center. We didn't get too far into Grignard reagents last semester. Grignard reagents are very important nucleophiles, specifically because they are carbon nucleophiles. We will talk about Grignard reagents more later on in chapter 23. However, let's just do a brief introduction about what these nucleophiles do. Essentially, if you have an alkyl halide, which we do know how to make, right? You can take methane and react it with Br2 with heat or light in a radical halogenation reaction. If you react it with magnesium with diethyl ether as a solvent, you can actually get an exchange of electrons to form a Grignard reagent. Now, what this Grignard reagent actually is, it's a carbon with a negative charge. I'm just going to flip that carbon around so we can actually see the ionic bond between carbon and magnesium. This is a very, very reactive nucleophile. And so that carbon nucleophile is going to be our basic reagent, right? It is looking at a C-1 that can be used with any, actually what's great about Grignards is it can be used with any type of carbon group, all right? It can be sp3 hybridized, sp2 hybridized, sp hybridized. So any of our sp3, sp2, or sp carbons can undergo this reaction. So let's go ahead and see. I like to just take the Grignard reagent and show the ionic bond already so I can remember that a Grignard reagent is a carbon ionically bonded with a magnesium. And then it will, again, react to attack the carbon of the carbonyl. Our intermediate will be oxygen minus and a new carbon-carbon bond. There's the new carbon-carbon bond that's made right here. Second step is always going to be a water workup so that we can protonate our alcohol. Very, very similar to lithium aluminum hydride or sodium borohydride here. Aldehydes and ketones will always be able to react with a Grignard reagent. The only thing, again, to watch out for is unsymmetrical carbonyls. When you have an unsymmetrical carbonyl, you could create in that first step a chiral center. And then that chiral center will be racemic once again because our nucleophile is attacking an sp2 hybridized carbon and therefore either top or bottom attack, always racemic, okay? So be very aware of that with our carbon nucleophiles. If you want to see a generic reaction, here it is. We have an R minus. Any carbon minus group there will attack the carbon of the carbonyl, and then a proton transfer in step number 2. Please note that this is always going to be step 1 and step 2. We cannot have water with a Grignard reagent because water would just be deprotonated by the Grignard and not have the Grignard attack the carbon of the carbonyl. The cyanide ion is also a carbon-based nucleophile and reversibly adds to a ketone or an aldehyde to form a cyanohydrin. So HCN is used. This is not a great acid. Hydrocyanide is actually very poisonous. It's kind of coincidentally the acid used in the thought experiment for the Schrodinger cat thought experiment, right? When Schrodinger said that an electron behaves with wave-particle duality, simply like a cat sealed in a box with hydrocyanide on a radioisotopic delay of hydrocyanide in a vial. So this reaction just is near and dear to my heart for that reason. Again, no cats were harmed in that thought experiment, but look it up, it's great. This reaction works better under basic conditions, so a catalytic amount of base is used. Usually the base that we see is KCN written underneath the reaction arrow. Mechanism for cyanohydrin formation under basic conditions. Our cyanide ion reacts, nice, and attacks the carbon of the carbonyl. And then HCN is used to protonate. Beautiful. The acid workup is not necessary since HCN serves as a source for protons. And since we're in a catalytic amount of base, then typically it's A-OK. So this is what we usually see for over our reaction arrow, and we get pretty decent percent yields. Either aldehydes or ketones will work with this cyanohydrin formation. Be very careful. Again, chiral centers are always possible with these reactions. We pretty much have to worry about chiral centers with our hydrogen or our carbon nucleophiles in general because we are typically only adding one thing to our carbon of the carbonyl, unlike our oxygen and our nitrogen nucleophiles, which made things that were either achiral because we added 2 oxygen groups that were identical, or looking at the imine or the enamine when we don't even create something that is sp3 hybridized. Cyanohydrin formation is also very good to use with lithium aluminum hydride or hydrolysis. These you do not need to know the mechanism for, but it is good to know the transformations. Lithium aluminum hydride will react with the cyano group, the nitrile, and it reduces that carbon nitrogen triple bond to a carbon nitrogen single bond and puts hydrogens everywhere. So there you have it. It becomes an amine, a primary amine. H3O plus will make that carbon nitrogen triple bond into a carboxylic acid. Again, transformations only, please. Last carbon nucleophile that we have is the Wittig reaction. Now, Wittig is a German name from the scientists who developed this reaction. The Wittig reaction is extremely important for organic chemistry because, like Grignard reactions, which are also very important, the carbon skeleton is modified. So we actually can make new carbon-carbon bonds and create new, bigger molecules, which is extremely important for drug design and biosynthesis. So ketones and aldehydes in this reaction are converted to alkenes with the formation of a new, hold up, carbon-carbon double bond. That's crazy. This carbon-oxygen double bond is going to be reacted with the ylide functional group for the Wittig reaction, which we'll talk about, and it formed a new carbon-carbon double bond. A phosphorus ylide, which is a carbon atom that acts as a nucleophile, and that carbon atom is also attached to a phosphorus. A ylide is a neutral compound that contains a negatively charged carbon atom adjacent to a positively charged heteroyl atom, typically a phosphorus, is the one that we're going to use. This mechanism is similar to a 2+2 cycloaddition between the Wittig reagent and the carbonyl compound. So we do an intramolecular cyclization reaction first, and then we'll do an intramolecular fragmentation. So the 2+2 cycloaddition occurs when the carbon of the nucleophile, carbon of the ylide, attacks the carbon of the electrophile, and then the oxygen carbon double bond, instead of going to be a lone pair, actually makes a new bond with the phosphorus. And then we have a collapse. The phosphorus carbon bond becomes the pi bond between the two carbons, and the oxygen then kicks up to make a new oxygen phosphorus double bond. Let's look at that again. Collapse to make a new carbon-carbon double bond. Collapse to make a new oxygen phosphorus double bond. We call this step a fragmentation rather than a loss of a leaving group because we are doing an elimination at the same time as a loss of a leaving group. So the formation of an especially stable triphenylphosphine oxide is what's driving this equilibrium forward to the alkene. Remember, alkenes are not as stable as ketones or aldehydes. Carbon-carbon double bonds are not as stable as carbon-oxygen double bonds. So it's really this triphenylphosphine oxide that is driving the reaction forward. How do we make the ylide? How do we make that reagent? Is we start with an alkyl halide, and we will use triphenylphosphorus and butyl lithium. Butyl lithium, again, is a base. It's a butyl group with a lithium attached to it. Don't forget, lithium to a carbon is an ionic bond. So really, it's a carbon with a negative charge, right? What we see down here as well. Sometimes, though, that is written where we have the bond between the lithium and the carbon, and I don't want us to get confused that it's a covalent bond. It's not a covalent bond. Butyl lithium is a very reactive carbon base. All right, let's just go through this mechanism. First thing is an SN2 reaction, backside attack. So you do need to realize that specific alkyl halides will better undergo this first step. Primaries are much more susceptible to be Wittig reagents than secondaries. You can use a secondary, it's just not as good. Very, very slow. And then butyl lithium creates that carbon nucleophile by deprotonating it. Why that reaction is better, even though both carbons are effectively sp3 hybridized, is because there is resonance stabilizing the Wittig reagent. Wittig is particularly useful because it installs carbon-carbon double bonds in place of the carbonyl. And the Wittig is stereoselective. So Z alkenes are typically favored in this reaction. Good to know. Z alkenes, cis, right? But if the Wittig reagent contains an electron withdrawing group, then the E alkene is the major product. So that's good to remember. If you have installed a electron withdrawing group or a phenyl group, something with pi bonds, typically those groups are repellent to the other half of our aldehydes or ketones. So that's where E or trans is the major product.